Okay, so I'm going to discuss today how do we obtain a representation of the Koopman operator in matrix form. And in order to pursue this, we're going to use the device called Carleman Linearization. Carleman was a very famous mathematician in the early 20th century, and he actually discovered this initially, I believe, without knowing Koopman's work, but pretty soon somebody pointed out to him that Koopman has done some related work, and then Carleman actually cited Koopman's work in his own paper. So let's get going right away. So we're going to take a broad class of dynamical systems. It's pretty broad. It's not certainly not all of them. We're going to work with analytic dynamical systems in Rn. So we're going to have a vector x and its time change x dot as the vector field f of x, and we are going to expand this into monomials. So ck is the kth coefficient, and xk is the kth monomial, where this boldface k is really an index for a vector of integers k1 to kn. So that's a monomial, and so for every single element of that vector, the vector field itself is just a linear combination of these monomials. And so let's for a moment think of these monomials as basis elements. So you can represent various functions using sums and of these monomials over coefficient ck. And I should point out that the coefficients here are real, as opposed to what we've learned in Koopman mode expansions. The coefficients can actually be complex, but here we are considering real coefficients. And so think of the monomials for a moment as basis elements. So we can represent many functions, a good class of functions, as finite sums over these monomials. Now, I should point out that one has to be a bit careful here, because of course, if one takes a look at the space of all analytic functions on Rn, that actually doesn't really have a basis. But let's put that technical aspect aside for a moment, and we'll try to apply the linear operator to this linear operator f dot grad, which we know is our generator. That's the generator of the Koopman evolution. And we'll apply f dot grad to a single monomial here, and we're going to obtain f dot grad of this monomial. Let's look at how this goes. If we take the gradient, we're going to have a sum of terms. Each of these terms is going to have a differential with respect to a particular element of this vector of partial derivatives. So let's say the lth. So if I select the lth term here, then the result is going to be xl to kl minus 1 multiplied with kl. So I've just differentiated one of these with respect to xl. So I differentiated xl to kl with respect to xl, and this is what I got. And the rest is going to stay the same. So there's this product of the rest of these terms on their own powers for m not equal to L. And then we have f dot that. So this is f right here. This is f. And of course, we have to sum over all L is equal 1 to n. So all the different elements of the gradient are producted with different elements of the vector field. So this is the lth element here, and this is the expression that we get. So that's a somewhat long story that at the end of the day says, here are some monomials in here, and there are monomials in there, and products and sums of monomials are polynomials. So this sum here consists of some coefficients multiplying some monomials. So again, I've stayed in the same class of functions which are monomials. So let's say we order the monomials somehow. There are various ways of doing this. One of them is lexicographic. There are a variety of ways of ordering the monomials. So this set of monomials is actually countable, right? So it's indexed over all these indices k1, k2 to kn, but that's a countable set of indices. So we should, in order to order them, we should map them onto n, and so we can write them into basically a vector. I'll show an example very soon of this. And so we are going to write yj for the jth monomial, and then we're going to have this infinite dimensional matrix representation of f dot grad. We're going to denote that by C. I mean, maybe just a little reminder that an operator acting on a basis vector can be represented as a matrix. Let's say that I want to do something like matrix A acting on a basis vector 0, and then I have zeros here, and then I have 1 at the jth place, and then maybe I have more zeros. So let me just for a second erase this and redo it. So let's say A acts on this vector that is a basis vector of coefficients 0, 0, 0, 0, 0, 1 at the jth place, and then 0, 0. This is clearly going to result at picking of elements of A, right? So we're going to have a little a is an element of capital A1j, A2j, all the way to a nj, where now 1, 2, and so on represent the rows, and j, of course, represents the column. In other words, if I want a matrix representation of this operator A, I feed it a basis vector in my vector space, and then I will find the jth column of A. So a very similar thing can be done with the infinite dimensional operator, f dot grad, and that's the trick that we are going to use this here and find this matrix C, which will be the matrix representation of the generator of the Koopman operator. Here we're working with monomials, so everything is smooth. The generator is acting on smooth functions, so everything is okay. All right. Now, on the other hand, if we write out the differential equations for yj's, remember yj's are these monomials. Yj's are, some of these ordered in some fashion. So if we write it out, we'll get y dot is by. How is that? Well, we calculated yj dot here, and we found out that it's the sum of monomials multiplied by some coefficients. So that's going to constitute the matrix B. So if we order monomials in the vector y, if we don't operate on their coefficients, if we order monomials themselves on vectors y, we get y dot is by, right? But if we act on the coefficients, just like I've shown for the operator A for that matrix, then we get a matrix C, and the B and C are related in the sense that B, which we are going to call the Carleman matrix, is just the transpose of C. Okay. Since F is a polynomial vector field, the number of non-zero elements in each row and column is going to be finite. This should really be non-zero, not non-empty. All right, so it's instructive to do an example. So we're going to consider a typical nonlinear system. This one is x dot is equal to minus mu x plus x squared, where x is element of R. So just a scalar. This system for, let's say, mu positive has the state space that looks something like this. So there is a fixed point at 0, and there is a fixed point at mu 0. And so the fixed point at 0, if mu is positive, like it is in this plot here, is actually stable, and the fixed point at mu is unstable. And clearly, this system has more than one equilibrium. The Bayesian of attraction of equilibrium 0 is between mu, but not including mu, obviously, minus infinity. And then the Bayesian of repulsion of mu is between 0 and plus infinity. So we have multiple fixed points in this example. And so let's work on the representation of the Koopman operator in this case. So x dot is equal to minus mu x plus x squared. Let's, in this case, we have a scalar x, and so it's easy to order the monomials. The jth monomial is just going to be x to the power j. So we order monomials as 1, 2, 3, 4, and so on by the power. And so the generator, let's write it out. And that A, the operator A, is f dot grad. So that's f minus mu x plus x squared grad, partial with respect to x. So we have just one coordinate. And so for j bigger than or equal than 1, we get A, so this operator acting on xj, to be minus mu j xj, right? So that's just this acting on xj, producing a j minus x to the j minus 1 times j, and then multiplying with this. So minus mu x times j x to j minus 1 produces this term. And then another term here is produced by multiplying the same thing with x squared. So that's gonna give us a j, which arises from differentiation, x on j minus 1 plus 2, which gives us a j plus 1. So A acts on the monomial xj like this. And so if you take a look at the coefficients here, they're minus mu j and j. And so according to our prescription, this should be sitting in the jth column. So let's look at the matrix C according to that prescription. Here is minus mu, that's this one, times 1, and here is 1. So right here in that column. Then we should go to the second one, should be 0, minus 2 mu, because j is 2, 2, and so on and so forth. This is actually showing the first n rows of the matrix, and the matrix continues in this direction, obviously, and in that direction. It's an infinite matrix that has diagonal terms shown here, and then below diagonal terms shown down here, right? So that's actually the matrix representation of our Koopman generator. So that's nice. Now, of course, if instead of acting on the coefficients, you acted on the monomials themselves, so you had a vector of monomials, then you see that, let's say for j is equal to 1, this would be x, and this would be x squared. And your vector would be, your vector itself would be x squared, and so on, right? And so you see that in that case, you would have minus mu times 1 and 1 acting respectively on x and x squared. So these coefficients minus mu and 1 will actually be in the first row, not in the first column. So if you wrote it as Carleman did, as y dot is equal to by, where y is actually the vector of monomials, then you would get b to as a transpose of c, and c is the representation of the Koopman operator in the quote-unquote basis. Although, as I said, analytic functions don't really possess a basis, but if we stick to a finite domain, for example, something that included both fixed points over here, then we would have actually a basis of polynomials. It would be perfectly fine. But anyhow, this would be the representation of the Koopman operator in that basis. And as you're going to see as we go, that's the essential element in constructing numerical approximations. This is analytical, but constructing numerical approximations is a selection of the basis. So the selection of the functions. Today, they are very often called a library of functions, because who told us that we need to choose monomials? We could have chosen x, sine x, exponentials, whatever we wanted. The reason why we chose, why Carleman chose polynomials was that that he started from analytic vector fields, but it's not actually true that the evolution of analytic vector fields can be well approximated by polynomials. So it's not entirely clear that that's a good choice, and we will discuss the choice of the observables that fit into our basis of the library of observables as we go, and especially in fact already in the next lecture when we talk about numerical implementations. So now we are at the point where we understood the Carleman linearization. And we understood what's its connection with the Koopman representation on a monomial basis. And so so now we can differentiate the nth monomial xn to obtain n x to n minus 1 times the vector field minus mu x plus x squared. And that's going to give us minus n mu x to the n plus n x n plus 1. And so you see, as I pointed out, that the nth row of the matrix actually reads minus n mu n and 0 everywhere else. So I pointed this out on j is equal to 1 case, but that's actually stated here and computed generally. Okay. So we're still working with this vector field here. And the next thing we're going to observe is that minus n mu is an eigenvalue of the matrix C. So we are in fact going to produce an eigenvector associated with that eigenvalue, and then we are going to use this to construct an eigenfunction. So the claim is that minus n times mu remember mu is the coefficient, it's a fixed parameter, is an eigenvalue of the matrix C, and therefore an eigenvalue of the Koopman generator, f dot grad. So, take n is equal to 1. So I would just like to show that minus mu is an eigenvalue. And here is an eigenvalue eigenvector equation. So if our matrix is C, then we have C, minus lambda I, but lambda is minus mu, times A, which is a vector of coefficients. That turns out to be an infinite vector of coefficients because I have an infinite countable number of monomials. And that equation, we're going to see in a second, is satisfied by this vector. So in the first position, I have A1. In the second position, I have A1 over mu, and so on. So let's look at C in the first row. So you would get something like, from here, so we get something like minus mu times A1. So I'm multiplying this C with this vector that in the first two positions has A1 and A1 over mu. And then it has some other elements here. That's what I'm doing. And so I have minus mu A1 plus mu A1 over mu. You see, the only element in the first row of C is minus mu, so I multiplied that with A1. And then in this setting here, I had also plus mu, right? I, and so I have A1 minus mu, A1 over mu, and that of course gives me, I'm sorry, I don't need to have the mu here, just a second. Hello, correction. It gives you minus mu A1, that comes from C multiplying the first element of A. And then I have the plus mu A1, which comes from this part multiplying. So this is the identity matrix, infinite identity matrix, multiplying the first element of A, and that is clearly 0. So far, so good to start with, but if we continue doing this for the second row, the third row, and so on, the result is the same. In other words, we get all of these terms to be 0. And therefore, this equation here for minus mu, for the eigenvalue minus mu, is solved by this infinite vector. Okay, so what that means is that I can take this infinite vector of coefficients and I can form a function out of it, phi of x. So let's do that. We have a1x plus a1 over mu x squared plus a1 over mu squared x cubed and so on. So I'll take a1x out, and then I get 1 plus x over mu plus x over mu squared and so on. And this phi of x, according to our theory, should be the eigenfunction of the Koopman operator. We'll verify that independently. But let's for a moment concentrate on the fact that if x over mu is bigger than 1, then this seems perfectly fine. This is a geometric sum and geometric series. And so I can definitely sum this up, even if it goes to infinity. In fact, a geometric series, if you get 1 plus r squared, the result is going to be 1 over 1 minus r. So my r is x over mu, and here is a1x. So I obtain a1x times 1 over 1 minus x over mu. So I sum it up, at least for x over mu less than 1. I sum it up, and this is phi of x. As I said, I'll verify that this is an eigenfunction in a moment, but it should be according to the fact that we have just represented the operator as a matrix, and we found its eigenvector, and that eigenvector corresponds to this eigenfunction. So it should be an eigenfunction, but as I said, I'll verify this. But what is interesting, and what is going to come out, is that, look, this expression here is actually valid for all x, be it minus infinity, except for 1. When x is equal to mu, that's precisely at this fixed point, then the denominator is 0. And so it's not going to work there. But everywhere else, it's a perfectly fine, finite function. So it could be computed in principle. From data, I mean, I didn't give the full set of recipes on how to compute eigenfunctions from data, but believe me, for now, and I'll present this in the next lecture. Now, the eigenfunction that we discovered is valid for the whole interval x is minus infinity to mu, that's an open interval, and mu to plus infinity, so everywhere except for here. So that's interesting, but let's do the calculation just to verify that phi is indeed an eigenfunction everywhere, so that nothing goes wrong. So in order to do that, we'll need to prove that phi dot is minus mu phi. This is an eigenfunction equation with lambda equals to minus mu being the eigenvalue. So let's do phi dot. Remember, phi itself is a1x divided by 1 minus mu over x. So we're going to differentiate this in time, which means we're first going to differentiate this with respect to x, and then multiply it with x dot. So this is x dot. First, we differentiate the numerator. So that's just going to give us a1 divided by 1 minus x over mu. And I do have a typo here. I didn't mean to say mu over x. I meant to say x over mu. So 1 minus x over mu is here. And then the second one, I copy a1x. And then I differentiate the denominator. That gives me 1 minus x over mu squared with a minus sign. And then I differentiate this with respect to x. That gives me minus 1 over mu. Okay, so I take x out of that expression, put it up here, obtain minus mu plus x for this, and then I sum this up. The denominator is going to be 1 minus x over mu squared. I need to put 1 minus x over mu over here then, if I square the bottom. 1 minus x over mu plus x over mu is 1. So I have 1 minus x over mu over here, plus x over mu, that gives me 1, divided by 1 minus x over mu. Now, of course, if I now take mu out in front with the minus, what is left over here is 1 minus x over mu. That reduces 1 minus x over mu squared, and I obtain the result, minus mu a1x divided by 1 minus x over mu. but a1x divided by 1 minus x over mu is precisely phi. So I get minus mu phi, and therefore I have proved that the phi that we found is indeed an eigenfunction to the Koopman operator at eigenvalue minus mu, because it satisfies this this linear equation. And so there are a couple of things to notice here. First, we found a quote unquote global eigenfunction that everywhere except at this fixed point linearizes the dynamics. And this is despite the fact that we have more than one stationary state here. So in the previous discussions, in the previous use of eigenfunctions, I restricted to basin of attraction and discussed the stability. But this analysis gave me here something global, because this has two fixed points. One of them has a basin of attraction, the other one has a basin of repulsion, right? So backward time attraction. Of course, the fact that we found an eigenfunction in this basin is going back to global linearization theorem we have discussed earlier, but it gets a little more interesting. So suppose that you had no knowledge of what your dynamics actually was. And suppose that you know or have a way of calculating phi directly from data. And we'll show how to do that. There are a variety of different methods, numerical methods on how to do it. And okay, in Koopman theory, you immediately know that if you find phi, it satisfies this equation. But let's suppose that you're dissatisfied with this particular representation, and you want, a nonlinear representation on the whole domain. You don't want this this aspect where you're not defined at mu. Suppose you want a nonlinear representation everywhere, and your measurement is really x, not phi. You have just computed phi from data. Your measurement is x, but you have no clue as to what equation it satisfies. So let's see whether we can discover what equation it satisfies, or what equation the evolution of x itself satisfies. So let's write, so here is phi as a function of x. Let's divide this expression by x. We get 1 over x at the bottom minus 1 over mu if we divide by x. And that will mean that 1 over phi will be 1 over x minus 1 over mu. Fair enough. So therefore x is going to be 1 over phi minus plus 1 over mu. That is actually a typo here. And that is going to give me that x is mu phi divided by mu plus phi. All right. So now now I got x as a function of phi. And by the way, phi, I'm going to maintain that I know phi only numerically. And if I know phi numerically, I also know phi dot. Phi dot is minus mu phi. So let me write x dot as a function of phi and phi dot to start with. So that's going to be mu phi dot divided by mu plus phi. That's differentiating the top. And then the bottom is going to give me minus mu phi. So I'm keeping mu phi on the top, divided by mu plus phi squared. And then again, multiplying phi dot. So this is derivative with respect to phi, and then multiplying it with phi dot. And so now if I note that phi dot is minus mu phi, I obtain minus mu squared phi mu plus 5 here for the first term. And then plus, because phi dot is going to give me a minus mu phi. So minus and minus are going to turn into a plus. Mu phi squared divided by mu plus phi squared. And so looking back at the definition of x, I get that this is minus mu x, because I have this mu squared at the top, but mu plus phi gives me the rest. And then this is precisely x squared. So what I discovered from data this time, remember, I didn't assume that x satisfies this equation. I discovered a globally valid evolution of x in a nonlinear form parameterized by mu. So now if we wanted to pursue bifurcation analysis, of course, for mu less than 0, the dynamics is different than for mu bigger than 0, and we get bifurcation at mu is equal to 0. We can do it with this form of the equation. We could, of course, do it with the other form as well, taking into account the nature of phi itself, the nature of the function, but certainly directly from data, computing phi, and then inverting phi as a function of x to obtain this formula here, we can get a nonlinear evolution equation that is valid globally and nonlinear. So this is quite important to know. In fact, that once you compute eigenfunctions from data, that you could also get global nonlinear evolution equations, if you wish. Obviously, if you wish to do so, if you actually want to get this particular parametric representation in polynomial form, you could certainly do that. Now, this has caused recently some confusion in the literature. There is a paper that just came out in no other place than Nature Communications, in which the authors don't quite realize that Koopman eigenfunctions can be used to provide, in the way I've just described, the global nonlinear representations of the data. So despite the fact that one can use Koopman operator theory and Koopman eigenfunctions to provide linear representations, it's certainly not restricted to that. And it's been used in many papers as essentially for nonlinear representations. For example, people have discovered nonlinear models using the algorithm called Cindy that was proposed by the authors from University of Washington, Nathan Kutz and Steve Brunton and collaborators. So anyhow, there is some confusion in the literature on this fact, but hopefully this particular analysis can clear that up. And this is where I'm going to stop today and discuss numerical implementation in the next lecture.